In this video, we introduce our paper ISPIL, Interactive Sub-Goal Planning Imitation Learning for Long Horizon Tasks with Diverse Goals. We propose interactive sub-goal planning imitation learning, ISPIL, that trains a hierarchical policy where the high level provides a reachable sub-goal, and the low level provides actions towards completing the sub-goal. The demonstrations are collected based on novelty estimation of the state. When a state is detected as a novel in the high-level policy, the human has to provide the meta sub-goal data with information about the causalities between sub-goals. If the novel state is detected in the low-level policy, the human has to provide the physical robotic action. After the demonstrations are collected, the policies are trained with their respective data. Let's focus on the key information required for the meta sub-goal data. First, we need to determine whether a sub-goal is satisfied in a given state. Next, we consider its dependencies on other sub-goals. We also examine its reachability, whether it can be performed in the current state. And finally, its preconditions, meaning the other sub-goals that must be completed beforehand. On the other hand, we have the low-level demonstrations, which consist in physical robotic actions required to reach a given sub-goal. We evaluate ISPIL in simulation in a kitchen-like environment over two setups, a simple one with 3 ingredients and a complex one with 6 ingredients. With those setups, we designed 4 cases where the final goal is to cook certain ingredients and put it on the plate. From case 1 to case 4, the complexity increases by varying the final goals and increasing the sub-goals to finish the tasks. We aim to answer if ISPIL improve accuracy while reducing demonstration burden. How robust is our method to disturbances? And if our method generalized to diverse goal with various complexities? We compared our method with other baselines that employ some of the characteristics that ISPIL has, such as hierarchical architecture, meta sub-goal data, and interactions. All the methods were tested in the 4 cases explained above, and we obtained the following learning curves demonstrating that our method is more accurate and demonstration efficient than the others. We verified the robustness in ISPIL in weak disturbance, which changed the initial state to one that was already presented during training, and strong disturbance that changed the position of cooked ingredient in the middle of the episode. To test the generalization capabilities, we tested the methods in other final goals different from the ones that were used for training the policies. These graphs show that only our methods are capable of accomplishing final goals that were not explicitly demonstrated. We also verified if it is possible to implement ISPIL in a real-world environment by training and testing a final goal where a cantaloupe and watermelon have to be cleaned and cooked before putting them on the plate. The demonstrations are given by using a gamepad and a tablet. When the robot's high-level policy detects a novelty, it collects meta sub-goal data. As previously explained, this data includes information about satisfaction, dependencies between sub-goals, reachability, and preconditions. The process begins with the final goal and works backward until a reachable sub-goal is identified. The robot continues the autonomous execution. And when the low-level policy detects a novelty state, the robot actions are given using the gamepad. We compare ISPIL and GCBC. The robot has to put the cantaloupe in the sink, activate the sink, put the cantaloupe on the pot, activate the stove, and put the cantaloupe on the plate. Similar steps are followed for the watermelon, except that the sink and stove are already activated. The results demonstrate that our method achieves a success rate of 93%, significantly outperforming GCBC, which achieves only 13%. This concludes our method overview. For more details, please refer to our paper. Thanks for watching.